In decentralized artificial intelligence systems, the protection of sensitive data and model outputs has become increasingly critical, especially in healthcare and finance domains where AI-driven diagnostics and decision-making involve handling highly confidential information. Researchers from Nesa address this concern by developing a comprehensive security framework leveraging multiple techniques, including zero-knowledge proofs, consensus-based verification checks, split learning, and hardware-based trusted execution environments. The primary aim of this research is to enable the secure democratization of AI through scalable, high-security frameworks tailored for distributed environments. At its core, Nesa's security approach depends on understanding and mitigating data security and privacy issues specific to distributed inference, focusing on balancing robust protection and performance efficiency. Researchers address these issues in two critical scenarios. Firstly, the critical inference scenario entails providing maximum levels of security and privacy to situations demanding strict protection. Applications here, including medical diagnoses and high-value transactions, involve computationally expensive protocols to maintain accuracy and data security. Here, zero-knowledge machine learning and homomorphic encryption, traditionally challenging in distributed setups due to heavy computation costs, have been applied strategically through techniques such as state-of-the-art zero-knowledge decentralized proof systems, ZKDPS, for enhanced effectiveness without incurring inefficiencies in full-fledged ZKML designs, thereby building custom SHI implementations called sequential vector encryption. Scenario 2 encompasses less demanding environments, general inference, by recommending Nesa's verification methodologies via CBV, ensuring faster task handling within high confidence rates across generalized low-intensity yet value-impactful inferral scopes. Despite slower lower speed-driven due integrity level requiring compromises or fewer based efficient secured settings, the model's input during phase build effectively minimizing reduction burden T performance optimal parameters resulting resource parameters essential operation deliver successful all header code. A detailed introduction for respective process referenced individual specified ladder is directly formulated. Below ladder explanations formal adaptation basis security demands specifically modeled eventual safeguard formulation. Due to increasing calls from important developments incorporating inherent substantial capacities available developing domains decentralizing platforms delivering superior edge operation domains eventually develop RUS. Here is a combined summary of pages 3 and 4 of the research paper. Nesa proposes a novel approach to security and privacy for critical AI inference, focusing on model verification and user privacy protection. The security flowchart in Figure 1 illustrates the orchestration of user data, AI models, and node runners, ensuring secure data and model transmission via sequential homomorphic encryption, SHI, and zero-knowledge decentralized proof system, ZKDPS, for model verification. Table 1 summarizes the proposed security and privacy solutions, categorized into critical and general inference scenarios. For critical scenarios, ZKDPS and SHI are recommended, while for general scenarios, consensus-based verification, CBV, and split learning, SL, are suggested. Additionally, the TEEBASED solution, NTEE, can be employed as an orthogonal approach. In critical inference scenarios, the significance of AI inference results necessitates the highest levels of security and privacy. Nesa's ZKDPS ensures model verification and integrity, allowing one party to prove to another that a statement is true without revealing any information beyond the validity of the statement itself. For data privacy, sequential vector encryption, SVE, is proposed, enabling computations on encrypted data without decryption. The paper highlights the importance of defending against adversarial attacks in decentralized AI inference environments, where nodes may behave deceitfully, compromising the integrity of aggregated results. ZKDPS ensures that nodes can provide proofs of honest execution to the central server or the public while safeguarding the confidentiality of their models. The challenge of fast inference of secure foundation models is addressed, given the slow inference speeds of foundation models and the need to incorporate security measures without compromising efficiency. Nesa's ZKDPS introduces new techniques to speed up the ZK process, ensuring the security of foundation model inference without compromising performance. In the context of decentralized machine learning, zero-knowledge proofs serve as a fundamental technique to ensure that each party is honest about their execution of inference protocols for foundation models. The process involves two entities, the prover and the verifier. The prover's objective is to demonstrate successful execution without revealing confidential information, known as the witness. This witness can encompass sensitive data such as model weights or private information that the prover wishes to keep hidden from the verifier. Zero-knowledge proofs have several advantageous properties, including completeness, special soundness, and zero knowledge. These properties guarantee that the proof will pass verification only if the prover is honest, while also allowing the prover to maintain the secrecy of their witness. Depending on whether the verification process involves a single round or multiple rounds, zero-knowledge proofs can be classified as either interactive or non-interactive, respectively. Interactive proofs naturally describe an interactive process where the verifier sends a challenge to the prover, who then responds to the verifier. If the proof is valid, the verifier sends a new challenge in the next round, and the process repeats. Non-interactive proofs, on the other hand, can be simulated by having the prover generate their own challenge. This is achieved by replacing the random variable in the challenge with a random oracle model or a hash function that operates on all the messages that the prover has sent so far, such as the Fiat-Shamir heuristic. In the context of Nesa's products, the technique of zero-knowledge proofs is applied to ensure that each computing node, prover, accurately executes the assigned computations on a foundation model or a part of the foundation model. The prover's commitment to the witness data, such as model weights, is implemented using the generalized Peterson commitment scheme. The prover then generates a proof of execution in a finite field F, which is transmitted to the central server, verifier, for verification. The verifier meticulously examines the proof to ensure the honest execution of the protocol by the prover, thereby validating the transaction or information under scrutiny. The semi-dishonest assumption is made on the central server, which is honest in aggregating results from each computing node and accurately reports the verification result. But the central server tries to glean additional information about parts of the foundation model at computing nodes. However, some computing nodes might be dishonest, potentially substituting their model with an alternative or outputting random data. We assume that the majority of nodes are honest, but acknowledge that dishonest nodes can collude. These adversarial nodes can arbitrarily alter their results, provided their behavior remains undetected by the central server. The paper discusses a cryptographic protocol that enables the prover to prove to the verifier that he or she knows a witness S in FD and a witness T in F, which are openings of the commitment 1 and the commitment of T 3, respectively, such that the inner product of S and Y equals T. This protocol is based on the Peterson commitment, which has binding, homomorphic, and zero-knowledge properties. In the algorithm, the prover first sends the commitment of S and T to the verifier, then the verifier sends a challenge E to the prover. The prover computes S and RT, using the challenge and sends them back to the verifier. The verifier checks if the commitments of S and T are consistent with the original commitments and the challenge. If the checks pass, the verifier is convinced that the prover knows the witnesses S and T. The paper also discusses the use of multilinear extension for zero-knowledge proofs of arithmetic operations. It explains how to express a d-dimensional tensor S in FD as a multivariable polynomial S via a transformation called multilinear extension. This transformation allows for the verification of arithmetic operations between vectors to be equivalent to the verification of the sum of multivariable, low-degree polynomial G. The multilinear extension enables the prover to prove to the verifier that he or she knows a witness S in FD and a witness T in F, which are openings of the commitment 1 and the commitment of T 3, respectively, such that the inner product of S and Y equals T, without revealing any information about S and T. In the context of verifying the execution of linear layers in foundation models, this paper discusses the sum-check protocol, aka the GKR protocol, which is an interactive protocol for verifying equations of the form H equals sum underscore X underscore 1, X underscore 2, L dots, X underscore V, in 0, 1, caret VG, X underscore 1, X underscore 2, L dots, x_v. The protocol consists of multiple rounds, with each round involving the prover sending a polynomial g_i, x_i, to the verifier, who then checks if h equals g_i, 0, plus g_i, 1. If the equation holds, the verifier samples a random number, r_i, and sends it to the prover for the next round. This process continues until the final round, where the verifier checks if g_v, r_v, matches the opening of the commitment by a proof system. The paper also addresses reducing linear layers to some check protocol. In this context, linear layers can be represented as matrix multiplication, and the ReLU activation function can be reduced to bit decomposition. The ReLU activation function is defined as a equals text sign z o dot text abs z, where z denotes the pre-activated tensor and a denotes the after-activated tensor. This decomposition allows for the application of the sum check protocol to verify the execution of ReLU activation layers in foundation models. The paper further discusses the use of lookup tables as another technique for zero-knowledge proofs of non-arithmetic operations. The lookup table technique involves the prover committing to a table of values and the verifier querying the table at a random index. The prover then needs to prove that the queried value matches the actual computation result, which can be done using the sum check protocol. In summary, the paper presents the sum check protocol as a means to verify the execution of linear layers in foundation models, and demonstrates how to reduce ReLU activation to bit decomposition and apply the sum check protocol. Additionally, it discusses the use of lookup tables for zero-knowledge proofs of non-arithmetic operations, which can also be verified using the sum check protocol. Zero-knowledge proofs of non-arithmetic operations in foundation models are achieved through various techniques, including bit decomposition, lookup tables, and sum check protocol. Bit decomposition is applied to ReLU operations, where the input z is decomposed into its binary representation, allowing the reduction of non-arithmetic operations to arithmetic operations. The sum check protocol is used to prove the correctness of this decomposition. Lookup tables are employed for non-arithmetic operations such as softmax and SWI-GLUE activation. A shared table is maintained by the prover and verifier, containing input and output vectors. The prover convinces the verifier that the input and output vectors satisfy certain relations by proving a subset relation, which is further reduced to a sum check proof. The integration of these techniques enables the construction of zero-knowledge proof systems for foundation models, comprising transformer layers and MLP layers. Arithmetic operations in linear layers and MLPs are proved using the sum check protocol. Non-arithmetic operations, such as softmax and SWI-GLUE, are proved using lookup tables, while ReLU operations are proved using bit decomposition. Table 2 lists the zero-knowledge proof techniques for various operations in foundation models, highlighting the need for carefully designed techniques for efficiency. Notably, ZKLLM is the first work to introduce zero-knowledge proofs to foundation models with tens of billions of parameters. At Nesa, the ZKDPS system is built upon ZKLLM and ZKDL, aiming to accelerate proof generation for decentralized large language models. Ideas for acceleration include leveraging the compressible property of LLMs using a small draft model and hardware acceleration through modern GPUs. Experimentally, the top one guessing accuracy of the draft model is as high as 82%, indicating potential for reduced proof generation time. Sequential vector encryption, SVE, is also introduced as a robust encryption method, focusing on select linear layers in modern LLM architecture. This framework considers the LLM as a sequence of vector space operators, applying homomorphic encryption to intermediate output vectors. This approach has the potential to be applied to other neural network architectures. Here is a combined summary of pages 13 and 14. Secure vector execution, SVE, is a technique designed to obfuscate the output of every operator in a sequence of large language models, LLMs, to prevent sensitive information extraction. This is particularly important for models relying on open-source foundation models, where intermediate latent spaces are available for study. SVE involves randomly transforming the outputs of every operator, making it difficult to interpret the intermediate vector representations. To achieve this, two main considerations are crucial. 1. Appropriately transforming each operator and 2. Ensuring secret sharing of transformation matrices. For linear operators, transformation can be achieved through a product of invertible transformation matrices and the original matrix representation. For nonlinear operators, such as the ReLU operator, symmetries can be exploited. For instance, the ReLU operator can be transformed as R equals P caret 1, RP, where P is a permutation matrix. To further obscure the transformation, a random vector with positive entries can be scaled, resulting in R equals M caret 1 underscore AP caret 1 RPM underscore A. To maintain security, secret sharing is employed to obfuscate the transformation matrices. This involves representing the single ith layer bias as bi equals raw, where A is a linear transformation and R is the nonlinear ReLU operator. By applying transformations S and T, the output of bi can be transformed to bi equals T caret 1 RC, where C equals TSA is a new matrix. This ensures that the transformation pair S and S caret 1 cannot be recovered. In general inference scenarios, Nesa proposes a consensus-based verification check, CBV, to ensure model verification and integrity. This approach leverages the collective agreement of multiple nodes to ensure correctness and integrity of model execution without revealing sensitive data. Additionally, split learning (SL) is employed to maintain data privacy by dividing the model into segments, each trained on different nodes, ensuring no single node has access to the complete dataset. The security flow of general inference at Nesa involves applying SL to encrypt the first few layers, followed by sharding and deploying the AI models to nodes with redundancy, and finally verifying outputs by consensus for integrity. In the context of decentralized machine learning, the Nesa framework employs a consensus-based verification approach to ensure the integrity of model execution across multiple nodes. This methodology involves redundant execution, output collection, consensus determination, and verification. Specifically, a subset of nodes computes the output for a given input, and the collected outputs are evaluated using a consensus algorithm to determine the agreed-upon result. This process facilitates the verification of model integrity and introduces a robust mechanism to detect and mitigate faulty or malicious nodes. In scenarios where model sharding is employed for scalability, Nesa adapts the consensus-based verification approach to accommodate the fragmented nature of model execution. Each node possesses a unique shard of the complete model, and redundant execution is performed by a designated subset of nodes for each shard. The outputs are collected and evaluated using a consensus mechanism specific to each shard, resulting in a shard-specific agreed-upon result. This process introduces computational redundancy, enhancing the detection of discrepancies or faults. Upon achieving consensus for each shard, the process ensures the integrity of the shard's computation before proceeding. The shard-specific consensus results are combined to reconstruct the final model output, ensuring the integrity of the complete model execution. Building upon traditional consensus mechanisms, the consensus-based distribution verification (CDV) strategy assesses the statistical distribution of model outputs across the decentralized network. This approach evaluates the aggregated statistical characteristics of the outputs, furnishing a sophisticated framework for affirming the uniformity and integrity of the model's behavior. The CDV process involves sharded execution and output synthesis, followed by advanced statistical aggregation and rigorous distribution comparison. Metrics such as mean, standard deviation, and higher-order moments are derived, and statistical methodologies like hypothesis testing and divergence measures are employed to evaluate the congruence between the observed and expected output distributions. This approach enhances security and privacy without direct comparison of individual inference results. In the context of Nesa's decentralized framework for large language models, enhancing the integrity verification process is crucial. The proposed consensus-driven verification (CDV) mechanism introduces an adaptive thresholding technique that dynamically adjusts sensitivity based on historical data and operational context. This approach focuses on distributional characteristics rather than discrete output values, aligning with the goals of enhancing model security and maintaining stringent privacy standards. By leveraging differential privacy methods during the transmission of intermediate representations from client to server, Nesa improves data privacy at the cost of inference quality. Nesa also utilizes split learning (SL) to address the complexities of data encryption within its decentralized inference system for large language models. SL partitions the computational model, allowing for data to be processed in parts without revealing sensitive information. Two key pieces of information: users' input data for AI inference and private model parameters are protected using TEAs, which provide a hardware-based solution for secure and private computations. Trusted execution environments (TEAs) effectively establish security and privacy within Nesa's decentralized inference architecture. Using TEAs, we can create secure isolation zones within the network's nodes, guaranteeing the privacy and accuracy of data and computational operations. Nesa designs a specialized version of TEAs, named NTEE, that best suits Nesa's scenarios with decentralized inference. NTEE is feasible for all node runners with or without GPUs. The advantages of TEAs include isolated execution, data privacy, and consistency and integrity. TEAs provide a secure enclave for executing computations, isolated from the rest of the node's operating environment. This isolation ensures that even if other parts of the node are compromised, the computations within the TEA remain protected. Data processed by the model can potentially be less secure if exposed to less protected parts of the system or network. TEAs encrypt the data within the enclave, ensuring that any information processed remains confidential. Even when data needs to be shared across nodes, it can be encrypted before leaving the TEA, ensuring that it travels securely across the network. TEAs can also ensure the integrity of the computations performed on each node. Through cryptographic techniques such as attestation, a TEA can prove to other nodes or external verifiers that the computations were performed correctly without revealing the underlying data. This attestation process allows other nodes in the decentralized network to trust the results from each node without having to access the actual data or model details, thus maintaining consistency and integrity across the decentralized model. Nesa, a decentralized AI provider, utilizes trusted execution environments, TEAs, to ensure secure and efficient AI inference tasks across multiple node runners. This approach leverages the low overhead and high performance of TEAs, which can be implemented on both CPUs and GPUs. By employing TEAs, Nesa eliminates the need for algorithm-based security measures, resulting in faster performance and enhanced security for data and models. The implementation of NTEE in Nesa begins with the initialization of a blank virtual machine (VM) TEA to each node runner, followed by remote attestation to verify the node's machine meets the requirements for a GPU TEA or CPU TEA. The supported types of TEA information are then sent back to the orchestrator. Once attestation confirms the TEA's security, Nesa securely transmits user data and AI model fragments to the node runner's TEA via an encrypted channel. Nodes execute AI inferences within TEAs and communicate directly with each other through secure channels. The orchestrator retrieves the aggregated results from TEAs securely and notifies the node runners to destroy each TEA. Nesa's NTEE paradigm for decentralized AI inference is illustrated in Figure 5, showcasing the high-level overview of the process. The use of TEAs in Nesa provides scalable and secure collaboration among multiple nodes, allowing them to pool their data securely for training and inference while maintaining data privacy and compliance. The destruction of TEAs after the inference tasks ensures no residual data leakage or unauthorized access. Nesa's decentralized AI system leverages trusted execution environments, TEAs, to ensure the confidentiality and integrity of user data and AI models throughout the entire lifecycle of computation. The system involves multiple TEAs across various nodes to run a shard of an AI model, requiring advanced strategies to ensure efficiency and security. In Step 4, each node runner's TEA performs a part of the AI inference using the model fragment MI on the data X, providing an isolated environment for secure computation. The computation within the TEA can be denoted as Y equals MI, X. For sequential tasks, the orchestrator sets up encrypted channels among the nodes with computation dependencies, allowing direct transmission of intermediate inference results. In Step 5, the final inference results YK are securely transmitted back to the orchestrator from the last node's T using an encrypted channel like SSH. After successful retrieval and verification, the T on the node runner is destroyed, ensuring that any residual data or model information is completely removed. Nesa's innovation in Ts involves communication optimization among multiple Ts, establishing preset secure communication channels among the Ts to minimize data transfer between the orchestrator and each T. This approach reduces latency and improves overall system efficiency. Direct communication between Ts is secured using encrypted channels to ensure data privacy and integrity during transit. To establish secure communication channels among the required Ts, Nesa employs a key exchange protocol, such as the Diffie-Hellman key exchange, to generate a shared secret key. From this shared secret key, a session key is derived using a key derivation function, KDF, which is used to encrypt the data transmitted between the Ts. Nesa's heterogeneous T scheduling strategy involves dynamic scheduling based on initial attestation results, determining whether a node supports GPU-T or CPU-T only. This approach leverages the strengths of each type of T, ensuring that computationally intensive tasks are handled by more capable nodes, thereby optimizing overall system performance. Nesa's decentralized AI inference system ensures efficient and secure performance across heterogeneous trusted execution environments, TEs. By dynamically allocating computational tasks, the system minimizes delays and maximizes resource utilization, enabling seamless scalability without compromising performance or security. This approach leverages the strengths of both GPU and CPU Ts, providing robust security measures and dynamic resource allocation to meet diverse computational needs. The system addresses significant security and privacy concerns in distributed and decentralized computing scenarios, particularly with the development of large language models and diffusion models. Nesa offers adaptive security and privacy solutions tailored to different scenarios. For critical inference tasks, a zero-knowledge decentralized proof system, ZKDPS, is recommended for model verification, and sequential homomorphic encryption, SHI, for data privacy. For general inference tasks, consensus-based verification, CBV, is proposed for model integrity, and split learning, SL, for data encryption. Additionally, Nesa's Trusted Execution Environment, NTE, provides a hardware-based approach that addresses both verification and encryption needs simultaneously. Future research directions include optimizing ZKDPS to reduce computational overhead and increase processing speed, developing ZK templates adaptable to various AI models, and building an automated framework that recommends and chooses the best set of security and privacy approaches based on specific user needs and application scenarios. This hybrid strategy allows for balancing security, privacy, and efficiency, providing users with flexibility in selecting the most suitable solution for their needs. The system's security and privacy frameworks are built upon various innovations, including ZKDPS, SHI, CBV, SL, and NTE. These components are supported by a range of research papers and studies on topics such as decentralized AI, zero-knowledge proofs, trusted execution environments, and secure machine learning. By continually improving the robustness, efficiency, and adaptability of its security and privacy solutions, Nesa aims to maintain its leadership in secure and private AI deployment. The authors draw upon a range of existing research to inform their approach to privacy-preserving training of encrypted data using split learning. Specifically, they reference the work of Tanveer Khan et al. On split learning, 29, as well as the Llama 2 model developed by Hugo Touvron et al. 30. The concept of differential privacy, introduced by Cynthia Dwork, 31, is also relevant to their approach. Furthermore, the authors acknowledge the work of Ruzba Benia et al. On privately fine-tuning large language models with differential privacy, 32. In addition, the authors reference the development of trusted execution environments, TEs, on GPUs, such as Graviton, 33, and the use of TEs for model privacy at the edge, as proposed by Fan Mo et al. 34. The authors also draw on the foundational work of Ralph C. Merkle on secure communications over insecure channels, 35. The author's approach involves the use of split learning to enable the training of encrypted data, while maintaining the privacy of the data. This is achieved through the use of a combination of techniques, including differential privacy and tease. The authors argue that their approach provides a more secure and private alternative to traditional machine learning methods, which often rely on the sharing of sensitive data. The authors also present a framework for privately fine-tuning large language models, which builds on the work of Rouzbeh Benia et al., 32. This framework utilizes differential privacy to ensure that the fine-tuning process does not compromise the privacy of the data. The use of tease, such as graviton, 33, is also proposed as a means of providing an additional layer of security and privacy for the training process. The authors argue that the combination of split learning, differential privacy, and tease provides a robust and secure approach to privacy-preserving training of encrypted data.